We're starting session number 3. Oh, there I am. And we're returning, at least from my perspective, a little bit more to chemistry again with an inorganic chemist by the name Ingo Krossing, who comes to us from the University of Freiburg. Ingo studied at the LMU Munich chemistry and also did his PhD there in 1997. Thereafter, he was a Frédérick postdoc in Canada, in Fredericton. Started immediately thereafter his independent career as a Liebig Fellow and later on as a Heisenberg Fellow at the Universität Karlsruhe, now renamed as KIT, before he became an assistant professor for a short stint in Switzerland at the EPFL, and then finally assumed his position as chair of inorganic chemistry at the University of Freiburg. His interests don't sound like hydrogen, but he will speak about hydrogen today. His interests cover ionic systems, reactive cations, ionic liquids, electrochemical energy storage, development of unified acidity and reducity scales. Inventing these new words, right? Making it really hard. Well, anyway, his title is From Hydrogen to Carbon-Based Platform Molecules. You could also say to organic chemistry. Chances and limits for its applications. Ingo, please.
Is it? Yeah, it is working. Sorry. So, thank you very much for the very kind introduction and allowing me to speak here. And well, it's kind of the energy transition session, and maybe. I guess I have to put it. Now it works. So there are some big discussions going on, and you see here there's hydrogen. You know, there you find it. What should be used for mobility? And I guess there was a psychologist over there who was not very fond of electric cars. And so let's have a look at this. I guess climate versus energy. Now climate is all about CO2, zero. Energy, fossil to renewable. Is it too simple? Well, let's look at this with a bit on the focus of mobility I've been thinking about quite a bit. And the reason I've been thinking is that these are the subgroups here, and I have one subgroup really for catalysis for e-conversion and the other one on batteries. And the energetic connections between those are some kind of like a Babylonic Verwirrung, so you get obscured, I guess, sometimes. Let me go back. What's energy? Energy comes from the Greek, and it's an active force, you know, light energy, kinetic energy, thermal energy, potential energy. The SI unit is a joule. And, you know, energy cannot be destroyed. It's just converted from one form to the other. And with the conversion, you can do work. And power is not energy. It's always mixed up. And the SI unit is a watt. And energy is not an energy source. Energy is converted, and the conversion can be used to store energy. And it can be physically, like in a flywheel or in a pumped storage, but it can also be chemical energy storage, and that's in chemical bonds. And if you want to do it renewable, well, dihydrogen, the hydrogen-hydrogen bond, stores a lot of energies, but people always forget also in a battery, you shuffle around bonds between the charged and the discharged states. The energy is stored in bonds. And again, the solar energy of ancient times is stored in the molecules that are within natural gas, crude oil, and so on. But this is the fossil source that you want to avoid. So is there an energy hierarchy? People tend to forget this because what we're using is pretty much not a very good idea. We take fossil fuels, we combust them, and we produce thermal energy. Thermal energy is then converted into kinetic energy, and we have conversion losses. And this, for a thermal process, typically is the Carnot efficiency, which is just dependent on the temperature difference between the hot spot and the cold spot divided by the hot spot temperature. And if you do it for a diesel engine, combustion at 2000 degrees Celsius, still the exhaust fumes are pretty hot at 500 degrees. In an ideal system, this gives 65% efficiency. That's what you have in the gas power plant, roughly. But under real conditions, load leveling, you're 25 to 35%, so pretty low efficiency there. And now if you couple processes, what happens if you couple processes? For example, if you take electrical energy, convert it to hydrogen, and back to electrical energy. We had been heard about this. Well, you need water electrolysis. We have been hearing about this. PEM, typically 60 to 70% with good conditions, load leveling less. Back, hydrogen to energy, then you need a fuel cell. Again, PEM between 35 and 60, again for load leveling and driving a car, it's much lower. So 60% is rather good already. If you combine those, the efficiencies need to be multiplied. So if you start with 100% renewable electrical energy, convert it into, ideally into hydrogen, you're at 70% of the energy. We forget about the 15 to 30% we lose by compressing it or liquefying the dihydrogen. And if you then set it back into a fuel cell, you're at 42%, so honestly more at 30 or 25%. So that's one of the backgrounds to look at this, I guess. And with this, I want to look at the question, if we harvest the renewable energy, maybe from solar, from wind energy, if we have it, so what's the best for mobility? Going through batteries, going electrolysis fuel cell, or combining electrolysis, CO2 capture, power-to-X processes to go to a syn fuel? Well, some things are missing. What about the round-trip efficiency for charging of lithium-ion batteries? It's not too bad, actually, roughly at 95%, maybe in winter a bit less, but still above 90%. That's not too bad. What about an electric motor? Well, it's pretty good, actually. If you have a large motor, it's much more than 90%, typically 96, 97% is the usual. And with this, we made a well-to-wheel analysis. Sorry for well-to-wheel. For my purpose, this is good enough. It's not cradle to cradle. But for the arguments here, if you put in the energy for the transport, this is the percentage of electrical energy used for mobility. 100% at the beginning. In your battery, end up 86%, so rather conservative with a lot of losses. After driving, 69% of the energy end up in your mobility. If you do the same with an internal combustion engine that uses an e-fuel, you start again with 100%. 44% end up in your tank, and because the Carnot efficiency is so bad, in the end, 13% are only used for the transport. And the fuel cell is somewhere in the middle, it's at 22%. Numbers. What do they mean? Well, let's look here. Let's now look for the CO2 output first. If you put the projection of the Fraunhofer ISE, well, I'm from Freiburg, in 2045, with the energy scenario by then, they are all almost carbon neutral. So, what about? Well, if you do the same distance, 100 kilometers, there's quite a difference in the electrical energy renewable needed to do 100 kilometers with a battery electric or with an internal combustion engine with an e-fuel. Let me put this into a thought experiment because it's hard to understand, I do think. In 2019, we had 46.5 million passenger cars with an average mileage of 13,602 kilometers. Let's take these numbers, multiply it by the number of cars, and think that all cars are running battery, fuel cell, or combustion. And these numbers come out. You see here the ratio is 1 to 3.5 to 6, which is pretty large. Well, the German energy demand in 2019 was 518 terawatt hours. That tells you to charge all cars for 1 year, it needs the buildup of 28% of the energy system in addition to the existing one, which is okay, I would say. Because now we're talking all cars. If you look for a fuel cell, despite the problems with platinum and iridium, additional 98%, you double it, with an e-fuel 170% on top of it. So what's my conclusion to this? Is there a preferred mode? Well, yes and no. We will need all, definitely. It's just about each for the best application. And there are cases where I cannot avoid it. For example, container ships, transcontinental airplanes, they will need synfuels, no doubt about this. Maybe intermediate ship distances with a fuel cell, cars, individual transport, definitely by battery, I guess. But still, it's about, and this is what I'm trying to say, it's balancing CO2 and energy, and it's too little thought together, to my understanding. With this, there's a lot of effort to make synfuel still, because a lot of methanol or related systems are needed for ships. And that's my standard slide here. So you take your renewable energy, you take point sources, CO2 from biomass, from fossil, you make direct air capture, you combine them with an efficient catalytic process and make my favorite platform molecule, that's methanol. Because you can use it for chemical uses, you can use it for mobility in ships or in planes, with the methanol to jet fuel process, or for local energy demands. Why? Because it's a nice liquid with a good liquid range and a pretty nice density. And these are the same numbers that Frédérick had, but not gravimetric. That's unfair, because 1 liter of liquid hydrogen weighs 80 grams. Now it's volumetric. And then it's not so good anymore, because liquid hydrogen has just 2.4 kilowatt hours per liter. Actually, the same problem with a hydrogen-fired power plant. The energy density per volume is much lower than that of methane, and therefore you have problems to develop the right gas power plants which are fired by dihydrogen. So methanol is not too bad, half of gasoline, so it's a nice platform molecule, and it's produced already in huge scales, 170 megatons per year, and it's a real platform molecule used in many, many, many applications, which is shown here. And also, the green or green air production is increasing if you trust methanol.org. And so the prediction is that by 2030, you have like 44 megatons of a green or green air methanol to be produced, for example, like here in the Haru-Oni plant, which is still very small, but likely to grow. And the main application, I digged out the numbers from Statista, is already now the number of ships that use methanol as a future fuel is increasing. That's 22, 1.4%, 23, 8%, 24, 9.7% of the ordered ships have now this alternative methanol storage. So what we really need is what is the optimal sequence to prepare a green methanol and derived platform molecules. This is what drives me since 17 years in the meantime, I guess, 18 years. And so the sequence here, I'm doing always calculations, I'm doing always thermodynamics as a background, is what I think, and what's starting on giants like Asinger and from the Anglo-American Society, Ola, with the methanol economy book. That's kind of one of those routes. You start with carbon dioxide and hydrogen, make methanol out of it, dehydrate it to dimethyl ether, and then in our case, we went for a long time to the direction of making the oxymethyl and dimethyl ethers. You have to consider that these plants are huge. This is a syngas production plant, produces 5,000 tons a day, 5,000 tons a day, or 1.8 million tons a year. And it operates at these temperatures, and it uses 200 tons of catalyst. So it's not allowed to be too expensive and too rare metals, I guess. My perspective on this is, okay, look, if you look at it, go for the thermodynamics. Why is the current process so efficient? Well, it's atom economic. CO takes up 2H2, makes methanol. It's going down in delta G, it's going down in delta H, and it's a single pass process, very straightforward. It's more complicated if you include CO2. You need an additional hydrogen molecule. You always produce water. You have a competing reaction, which is the reverse water-gas shift reaction, which is endothermic by nature. And since you have to go to higher temperatures for activity, the higher the temperature, the more it kicks in, and the more it produces a byproduct that you don't want. Then, for this process, delta G standard is at naught. So you have a true equilibrium there. You have to put pressure in. And this shows here in the equilibrium conversion as a function of temperature. You have to work here for temperatures because the catalyst systems are not perfect. And Robert Schlögl, really an expert here, always says, well, the catalyst is drowning because water is detrimental to the system because all the active layer is covered by water, and you need higher temperature to dissolve the water. And so water tolerance of the entire system is very, very important. Okay, when we entered the field, I have a background in organic chemistry. I like strange things. I like difluorine. F2 is a very nice molecule. It's very nasty, it reacts with everything. Because a lot of the catalysts that were all of the catalysts that were published were in an oxide matrix, oxides. And all the metals were permutated. But the oxide was not exchanged. And so we thought, what happens if we expose our pre-catalyst, so we make co-precipitation, calcination, and then the oxidic catalyst, if we expose it to gaseous F2. And we learned, okay, you change the system, you increase the number of active methanol sites, you leave the quality of the sites unaffected, which tells you that the apparent activation energy is unaffected. The reversible water-gas shift sites are deactivated. Here you see it, that the apparent activation energy goes up, and you get a better production. The problem, what does it, I wanted to show you this. This is a COX variation. That's the oxidation state is changed between carbon monoxide, 1.0, and carbon dioxide in incremental steps here. And this is what you see typically at integral conversion. At higher temperatures, you get this volcano shape, and the syngas system runs typically here at 1.1 roughly. This is the most active system. And you see here, this is the carbon dioxide line. The efficiencies are lower than for carbon monoxide. If you put in the fluorinated systems, all of a sudden this changes, and especially here, this highly fluorinated system has a higher selectivity, so the rest is reverse water-gas shift reaction, and higher productivities in the end for the methanol production. All good. Mechanistically, we have understood. We start with a precursor. We fluorinate the copper part with difluoride. The zinc oxide has some little tiny fluoride incorporations, which are very important because in the activation step, they are set free. And this is kind of the active system here, which is taking up dihydrogen as a shallow electron donor. This is filling the defect sites, and this is the place where actually carbon dioxide will be captured, and which is the starting point for the classical methanol catalysis process. However, copper zinc oxide is perfect in a synergism, but it's not long-lived. You need 3, 4, 5 years longevity of the systems. So we needed a support material, and here fluorine is sometimes nasty. So this is the thermodynamics for the interaction of the oxides with difluorine. It goes downhill. Zirconia, the classical material which made carbon dioxide hydrogenation catalyst, is not good. It's a fluorine magnet, and we thought, okay, maybe let's try iron. Iron works, has some problem, does some Fischer-Tropsch catalysis in the end, but the best is certainly the magnesium system. You have to believe me, it's fully characterized. And it's again the COX variation between here, carbon monoxide and carbon dioxide. And the black ones here are those which are non-fluorinated. And you see here, these fluorinated versions increase, and they again have the best activity for the pure CO2 stream, which is nice. And they are long-lived. This is a busy slide. This is a commercial CZA, aluminum catalyst, and it deactivates over time after 14 days on stream. And the same holds for the unfluorinated version in black, and the ZZZ is also a commercial copper-zinc zirconia catalyst. These fluorinated copper-zinc magnesia catalysts, they increase in activity, and after some time they stably reside higher than the other catalysts. This also follows from activation energies and other things we have shown by NMR, by XPS, by ACM, in the end, that it's the formation of magnesium difluoride or magnesium oxide fluoride, which has a rutile structure and which apparently has a support effect, which makes the system long-term stable. All good, but the people are afraid of difluorine. They don't want to work with difluorine. What to do? Well, there is another fluorinating reagent which is known to the people, that's NF3, because NF3 up to 200 degrees is rather doing nothing. You can really inhale it, there's medical grade. And we made up a setup where you can do the calcination and the fluorination in one step. It now runs also with a flow. And the point is NF3 has a global warming potential. You have to destroy it afterwards. Here, this is the destruction tower, but it works. And you see here, these are the ones fluorinated by F2. These are the ones in our Kafka apparatus fluorinated by NF3. And the performance is pretty much identical. This is what I really like. We learned something about particle sizes. They get a bit larger, the copper nanoparticles, with increasing fluorination degree. But still, with all this, we were also interested to learn about the mechanism. And for molecular chemistry, it's easy to do all kinds of DFT, ab initio, whatever calculations to understand this, which is more difficult. We teamed up with Richard Kettler at Imperial College, and I sent over David Jurado, and he made the calculation. He could get a realistic structure with vacancies, with interstitial sites. We could calculate the complete mechanism. What I wanted to show is just one thing really is that the mechanism is thought to be a formate-based mechanism. If you have a more realistic structure, you can find many formates, and we've seen them with drift studies. But you see here, there are more stable formate structures than the one which is relevant for the mechanism, and definitely what people see with drifts are resting state spectators, but they are not the true intermediates, unfortunately. Although we have made a complete operando setup. That's the almost last slide. We do the otherwise conversions as well, but after a long time in there, I say the more conversions you make, the more losses you have, and I think stay with methanol and don't convert it further. Methanol is a platform for many other things. Okay, so we have to harvest the energy, but we have to think of the combination of CO2 neutrality and minimal energy. Otherwise, we have to install way too many turbines. And I would plead first use electrical energy, then store it electrically, and then use it to convert hydrogen and use in all these processes where you might need it. One short number in the end. My coworker worked this out, and I thought it's really cool. We take the entire atmosphere and calculate, this is a number of tons of carbon dioxide. If you want to reduce it to the levels pre-industrial time, it's still 1.12, 10 to the 12 tons of carbon dioxide. And they say in the 2030s, you have to pay €100 per ton CO2 to sequester it and put it into the ground. Then it's still 112 trillion euros. Currently, it's a factor of 6 to 8 to that. On the way around, if you want to reduce 1 ppm of carbon dioxide from the atmosphere, it takes 0.83 trillions of euro. To put this into context, the gross domestic project of the USA is 25.5 trillion euro. The reduction, if you take all the money from this country just to reduce CO2, it's 30 ppm. So I guess we should better omit it. Thank you very much.
Thank you, Ingo, and also for the numbers that really make us think. Questions, please.
For the catalyst, zinc oxide makes these nanorods.
Yeah.
Are you considering these with a large surface and different facets?
No, what other people, what Robert Schlögl and others have shown, it's a zinc oxide overgrowth where you come from the zinc blend or what's type to a graphitic structure, and this is overgrown on the nanoparticles. There you have the effect, and there's the close distance from the zinc oxide to the copper, because then it's like a Schottky barrier, and you can insert electrons in there, and this is a starting point for the mechanism.
Further questions, please.
Yeah, if we look at that from an economic point of view, we know that at the moment we see green hydrogen onshore is something between like $6 to $8 per kilogram. Offshore, a TNO study has recently shown that it's even $12 to $14 per kilogram. Where would actually methanol end up in our level cost of energy calculations?
Methanol in the classical syngas process is fluctuating between 350 euros to 500 euros per ton. And I'd been in several consortia where they did a techno-economical evaluation, and if they set up an entire plant, they say it's going to be 600, 800 euro currently, and it's also a factor of the size. And if the size is large enough, it's going to go down. I think I even have one of those numbers in the backups here. It was a price, if you remember. No, I forget it. I thought I have it now. But it's getting there. But it's a number of size, and it's a measure also of the number of hours, of operating hours of water electrolysis. And what I learned is, okay, you can do load leveling with a PEM cell, but people want like 6,000 hours plus per year. So the Chooni power plant in Chile is running 6,000 hours a year because you have stable wind energy, and this is running okay. And so it's also associated with a number of hours where you can run the electrolysis there.
Martin?
The price you mentioned for methanol production, was that with CO2 taken from the atmosphere?
That was, yes. So
you take the CO2 out of the atmosphere and make methanol.
With direct air capture. So but this is a prediction, the long-term prediction then.
And that would be $500 to $800 per ton.
Roughly in this range. Depends on the time, really. So short term, more 800, 900, and then it can go down.
So that would be a circular economy, so to speak.
Yes, definitely, yeah. And we have to develop the technique anyway, because I guess some artificial withdrawal of CO2, unfortunately, will be necessary.
All right, that's a thought to be left with. Thank you very much, Ingo.
Okay, maybe not on the 19th. Okay, so we have another shift of gears. I told you this morning the way the sun is producing energy by fusing hydrogen to helium, and that it has been a dream for a long time that if we could do this in power plants, something like this, it could maybe solve our energy problems. Of course, we cannot exactly do what the sun does, because the first step involves a weak interaction, because protons don't you have to convert protons to neutrons first so that you can make helium in the end. So if you want to do fusion in a reactor, you have to start with a somewhat different materials that already contain neutrons like deuterium. And you all know about the huge projects underway that use magnetic confinement, like the ITER project in Cadarache was mentioned yesterday. And of course, these are all very long-term projects. And what we will hear about today now from Frédérick Bordry is a new kind of approach trying to make much smaller fusion reactors. And I think this will be as a very interesting and innovative new avenue. Now, let me briefly introduce the speaker. Frédérick Bordry is from CERN and from Gauss Fusion in Munich. His career, he graduated with a PhD in electrical engineering from the Institut National Polytechnique in Toulouse in 1978. In his early career, he first did teaching and work on energy conversion research. He spent several years in Brazil at the University Santa Catarina, and later he became a senior lecturer in Toulouse, where he obtained also a higher doctorate in science in 1985. And then in 1986, he moved to CERN, and there he had a number of functions and positions of increasing importance. So for instance, in 1994, he became the head of the power converter design and construction for the Large Hadron Collider project, which was then approved. In 2002, he became the head of the power converter group. In 2009, head of CERN technology department. And then finally, in 2014, director of accelerators and technology. And that is the department that is responsible for the operation and exploitation of the whole CERN accelerator complex, but in particular the LHC, but it is also responsible for new projects and technologies. And he held that function until 2020. And now he is in a new function as Chief Technology Officer at Gauss Fusion. And this is a green tech venture that was founded by companies with experience in industrial fusion technologies. And so I'm very curious to hear about the Gauss project, and welcome, Frédérick.
More. Thank you. Okay? Okay. Yes. Fantastic. Good afternoon. Thank you very much, Joanna, for this kind introduction. As you saw, that I did a long career at CERN in the technology, and I can explain why now I'm working in fusion. During this time also, I was CERN, I was responsible chair of the collaboration between CERN and ITER, because we are sharing CERN and ITER a lot of technology, superconducting magnets, control of a plasma of a beam, vacuum, power energy, radio frequency, and so on. We have almost the same technology, not the same goal, but the same technology. Today I will speak about fusion, and I will explain what we want to do and why it's important, and what can we do in Europe, because now the things are moving in US and China. It will be a pity if Europe, having all the technology, has not a word to say also. Then, as was said, I will not spend a lot of time. People said, fusion will work. I don't know if it will work on Earth, But when you are looking, the sun is working. All is fusion. When people are speaking about wind energy, solar energy, all is fusion. When we are speaking about oil in the earth is coming from fusion. All is coming from CERN, from sun. Sun. Sorry. then I think the fusion is everywhere in the universe, is the fuel of our life. Now, when we look at the sun, which temperature of the sun is 15 million degrees, and the fusion happens because we have a lot of 300 billion atmosphere, then the gravitational confinement is done on the sun. Okay, and we have this fusion with hydrogen, as mentioned by Joanna, but proton fusion, doing a fusion. The power density is small, with 300 watts per cubical meter. And if you want to do this on Earth, this 300 watts per cubical meter, if you want to have a fusion reactor of 1 gigawatt, you will need a huge apparatus. Then what we have to do, if you want to reach something that's feasible on Earth, we have to work and to succeed to have 2 megawatts per cubical meter. And some region to have up to 4, 5, 10, then we will have to see that we will have to have the material to withstand this kind of energy, this power per cubical meter. Okay, then to do fusion, you have 3 ingredients. You must to have extremely high temperature. You need to have a sufficient plasma particle density, and you have to have an adequate time to contain the plasma, not to lose this energy. Then there is 2 ways to do that: by gravitational, by magnetic confinement, or by inertial confinement. As I showed, that this we can forget is done in the star, in the sun, but we will not do on Earth. One word, then think this is due to nuclear transformation. We can see that this we have, according if you have very, very light atoms or heavy atoms, you can either, very well known, we have a fission with a large heavy atom. You have this energy of fission, and when you are with light atoms, you can do this fusioning the things and liberating the things. What we can see then, you have here the energy per fusion when you are doing this with hydrogen, energy per fission when you're doing with uranium or thorium, what can you do? And when you are looking that the energy released in a nuclear fusion is more or less 4 times greater than the fission reaction. You can see this on the drawing. This is 4 times. But also, when we are comparing what you release in terms of energy per kilos, then 1 kilo of fusion fuel, I will come back to that, is equivalent to 10 million of kilograms of coal you have to bring to your plant, or a liter of oils, or a cubicle of gas. You can see if we are successful, then in terms of consumption of fuel, is very dense. Now, comparing fission and fusion, then I think that it's true that fuel for fission are uranium, plutonium, or we can think about thorium. Fusion is hydrogen, what we are discussing today. After that, in terms of byproducts, when you have fission, you have all this used nuclear fuel that you can recycle, you can maybe transmute with a new generation 4. With fusion, what we have, you have helium that you can have exhaust and you can take and so on. It's not true, we have to be honest, that you have no at all waste. We have some materials, first of all, some materials that will be short-term, 100, 200 years of radioactivity that we will have to store for a given time. And to say we have no nuclear waste in fusion, we have to be completely open, honest to that. And at the end, we can see that obviously fission is energy production. A lot of countries, no more in Germany, but a lot of countries are still operating a fission plant and constructing a lot. And I think there is a lot of development also in fission domain, SMR, AMR, generation 4, small reactor, and fusion is under development. to come back, what is a fuel for fusion? If you are looking at the cross-section for the different fuel, definitely deuterium, tritium has the highest cross-section. If you want to do this, it will be nice to do with deuterium, deuterium. You can see this in terms of temperature. You will need order of magnitude. And if you want to do deuterium, tritium fusion on Earth, we will have to be at 150 millions of degrees. Already to do that, you will have to be 2 billion, 2.5 billion of degrees. And it's far to have that. And in spite of that, the cross-section is order of magnitude below. The good thing will be to be with proton and boron, what is very good because you have no neutronic, you have no need of tritium, but it's far for the time being, and we have not the cross-section. And as I said by Johanna, if you are looking proton-proton, we have the deuterium and so on, you have the cross-section proton-proton and so on is lower by a factor 10 to 24. Then forget to do that. It's good to done with the time and with the size, but cannot be done on Earth. Then this is definitely in the next period, in the next, I would say, century, the fusion will be made with deuterium and tritium. With deuterium and tritium, doing fusion, producing helium, according to that, and fast neutron with an energy of 14 MeV that we will use to heat water, helium, and so on, and to, after that, to transform electricity as a classical way, if you want, or to use as heat. Now, looking what is a fuel? What can we do with a fuel? I'm taking an example. If you want to do a fusion power plant producing 3 gigawatts of thermal, that is a 1 gigawatt electrical, the famous Carnot you had discussed before. Unfortunately, Carnot is against us, and to go better than 30%, 35% is difficult. Then if you want to do that, what we will need in terms of deuterium, more or less 0.3 kilo per day. That to say, if you have a fusion power plant working at a power factor of 85–90%, producing 8 terawatt-hours per year, more or less as a fission plant today or 1 gigawatt, producing between 7 to 8 terawatt-hours. You will need this 110 kilo per year. This is not a problem. Deuterium isotope of hydrogen is present, as mentioned, I think this morning already, in a water, 33 grams per cubic meter. I think we have enough deuterium for billions of years, and deuterium is not a problem. Now coming tritium. Tritium, you will need more or less also half a kilo per day with, to produce this 1 gigawatt electrical. That is say 150 kilo per year. Unfortunately, tritium is radioactive with a half-lifetime of 12.3 years. Then we have no tritium on Earth. We have a little amount by interaction of a gas with cosmic rays, okay, but we cannot exploit. Then now, the two sources, there is a source for military defense. They are producing the secret, but we know it's producing with an accelerator, bombarding a spallation source to doing, but producing order 1 kilo per year. Certainly the inventory for defense, some estimation, is also around 30 kilo in total in the world. And for the civil use, the production is made in heavy water reactor, CANDU, Canadian things, mainly in Canada, is small in India, but the main production of tritium is made is CANDU, and they are doing between 1 to 1.5 kilo per year. The present inventory is around 25 kilo. 25 kilo in 12 years, if you have no production, divide by 2. This is a problem. If suddenly we have a shutting down of this CANDU, what could happen, tritium will become a real problem. Then I think, conclusion, I think this is one of the key messages of my talk, that external supply of tritium for fusion power plant is not possible. It will be fantastic to have a fusion reactor to have all and to be able to put deuterium and tritium to fuel. This will simplify your reactor. You can put the magnet very close to the plasma and so on. Unfortunately, it's not possible. Then the tritium must be bred. We must have a tritium breeding blanket around our reactor and to do the closed loop for the fuel. And this is very important to know that every research, every company working in fusion not treating the tritium problem is not serious. I'm taking always the example. Imagine you have a very brand new car in 20 years and you want to start, but you have no fuel to put in it. It will be the case. If you are building a fusion reactor and in 20 years you are ready, but there is no more tritium in the world, imagine this CANDU we are stopping and so on. We have to do that. Then for me, there is two things. We need some tritium to bootstrap to start your things, few kilos. Then we have to think how to produce these kilos. There is some ideas, I can come back to that. And after that, to produce the tritium in a closed loop inside your fusion reactor. Then to say the fuel for a fusion power plant is not deuterium tritium, is deuterium lithium. Then we have producing the tritium through bombarding, then using this fast neutron in a lithium isotope, lithium-6, to produce helium and tritium. And you recuperate the energy. Then this is a lithium. Then we will need per year 110 kilo of deuterium and 300 tons of lithium to produce the things. 300 tons of lithium is big, not big, just to say that 1 Tesla is 63 kilo of lithium. Then we will need, a reactor will need 5 Tesla, 5 battery of Tesla, 5 lithium of Tesla per year. So this is not a problem. And the availability of lithium on Earth is okay. I think maybe they will need more lithium for cars than for fusion. Then to say that the breeding blanket is a critical mission for a fusion power plant. Then really we have to look at the key technology, that is a priority we have to look at, how to breed from the plasma lithium, how to do and to extract, to suck the tritium and to do that. And this is a lot of technologies. It can be useful also for hydrogen because all the permeation, all the treatment, all the things is synergy between looking this tritium breeding blanket and all this production of hydrogen in more conventional way and transport and so on. Then this is what we said. That now we need definitely. I take a tokamak, which is a mainly magnetic confinement. You have the vacuum chamber, we have the plasma. Around, you need to have this tritium blanket with enough volume, more or less is a thickness of 1 meter, all around your things, full of lithium to take the tritium and to, after that, to be able to do a closed loop of tritium. And this, as I said, is complicated. I will prefer, initially I said, oh, why not to put the magnet very close to things? You can do a very small reactor, but you will not have enough volume of lithium to produce tritium. This is, and to answer to you, Joanna, we look at how to do small things, but due to that, we cannot do. Maybe one day we will be able to do in parallel to a fusion reactor, a production of tritium that you can feed, but for time being, it seems not possible. Okay, so now to come back to the things that we have this magnetic confinement, inertial confinement, using laser to confine the particle, high density. This, I can say, this was, if you're looking, and this is with the magnetic, if you are looking the TRL, that you say the technical readiness level, definitely inertial confinement laser is lower than magnetic confinement. It was a big announcement of NIF in 21 when they did this with 192 laser on the small ball and putting 2.5 megajoule and they extract 3.2 megajoule. Well, it's fantastic, but you can do a shot per week. Now maybe they are doing a shot every day. But if you want to do production, you have to do that at 10 hertz. You have to produce a small ball. You have to align your 192 laser and so on. As I said, they are producing this because they look at on the plasma, they put 2.5 megajoule and recuperate 3.2 megajoule. They forgot to say that we have 192 laser consuming 300 megajoule. There is some room for improvement. Very good, maybe. But NIF was not done to do energy. NIF was initially for defense. And as we have in different things, in France, laser megajoule also is for defense. Okay, maybe one day we'll go to laser confinement or proton boron and so on. But for timing, in terms of TRL, is definitely magnetic confinement. There is a lot of work on that, different. Apart, obviously, I will come back to that. ITER, there is now a lot of companies looking at different configuration in magnetic confinement. I have to say the two main are the tokamak. The majority of number of private players or also public are looking at tokamak, and some are looking now with stellarator. I will not speak to all the other exotic hybrid things and so on. I think not everybody agree in terms of TRL. TRL is lower. It's not saying we have not to continue. I think for me, I always not to have any a priori, and research should be large. But if I have to bet my little money, if you have to do effort, I think it's a magnetic confinement with these two systems. Now, comparison between tokamak and stellarator. This I will come back. Initially, I will show a slide later. The stellarator was the first one. But the stellarator is a very complex animal with a different non-planar magnet, difficult to do. But the beauty of stellarator is a DC machine. You can keep the plasma forever in it if you are able to stabilize the plasma. The problem with the tokamak is a pulse machine. You have as a center a central solenoid that you are charging at full current, and you are discharging slowly as a transformer effect to inject a high current in the plasma. To say for big things, we are thinking that every 2 to 3 hours, you have to stop your plasma, you have to recharge your central solenoid, and you restart. And to recharge, let me be optimistic, 3 hours, you will need half an hour to recharge. Then in terms of duty cycle, it's slow. And during this half an hour every 3 hours, you need to have a storage of heat to do that. It's simpler in terms of magnet, more symmetrical magnet and so on. It was good to start with that. I will say today, for me, tokamak is a beautiful research machine. Stellarator will be the production machine because it's continuous. Okay, now people said fusion is always 30 years away. It was true, but I want to convince you that it was a tremendous progress the last 50 years and mainly the last 30 years. And to do that, there is a criterion created by John Lawson, that it is what we call triple product. It's a product of the density, the number of particles density of the plasma, multiplied by the temperature. And like I said, we will need 150 million of degrees. You can say it transform in kilo electron volt, mainly between 15 to 20 keV. And the energy time confinement. And this, when you have to reach above 310 to 21, where you will have fusion ignition, that the plasma will be, the fusion will be self-sustainable. Then if I'm looking at the different apparatus from the different years, and the big progress in the line, and now we have JET, we have ITER, that should go above this Q/1, when you have energy of fusion is higher than energy on the plasma. You will need more because you have to feed all the cryogenic system and so on. You will need at least factor 5 or 10. But it was a big progress last year. I like this slide showing the progress in comparison with other science. Obviously, with Moore law, with computer, and this is a progress with according to this criteria over the year from the 665, more or less 670 to up to this slide. I didn't find a new one after 2005 because it was nothing, really nothing. Was also a comparison with a big, what I like so much, high energy physics in terms of energy. Okay, LHC now is in operation. Now is this kind of saturation. We will see what will be the next, if it will be FCC, muon collider, and so on. We can discuss this is another subject. But, and now what is the next one? But to say that it was a lot of progress the last 50 years. We are not still at the level of this ignition, but we are not so far. And it's time to invest to go faster. Okay, this is a program EU roadmap for fusion. This is a ITER reactor, tokamak. Unfortunately, this is a EU roadmap, but ITER is a worldwide thing because you have also US, China, Russia, Japan, South Korea, and EU. For different reasons, we can discuss. So progress is not so fast as expected. It could be faster. I think management of ITER maybe could be improved. But it was the idea in Europe to have ITER, after that to have another one demo, producing electricity but not connected to the grid, and after to do that. I'm thinking now is too slow, and now these public things, what we are sharing, all the things doing that is not so fast. Now we have to go to fastest project, and we have to inject private money and to have private-public partnership, but private engineer and private money should take over from physicists and public money. Sorry to be like that, but okay, just to say that at the beginning was a stellarator. This was in the 52, more or less. This is Lyman Spitzer at Princeton laboratory. But at the time, it was built a small one, but when it saw too big, larger one, was not the technology of superconducting magnets, especially non-planar. This is now the beautiful things done with a W7X in Greifswald, north of things, put in operation in 2016, very well behavior, and now we have to go on bigger things. But this is a fantastic machine. I can see Joanna, I will be finished soon. Then to say that now there is a big, this is coming from a fusion, Fusion Industry Association, showing that now we have a lot of new companies, new private companies starting to do that. I think it's good because bringing private money in the domain. There is also now, I cannot resist, European Fusion Association, pushing also all the ecosystem, private company, cryogenics provider for fusion, but also new companies. And I want to not to spend too much time, but for the company I work, Gauss Fusion, it was a company created 2 years ago with something to focus really on the key technologies. The magnet, but I think magnet we know how to do, thanks to CERN, LHC, thanks to the stellarator W7X and so on. I think we have the methane. The main thing is the tritium, is really what we want to put all our effort to tritium. And this company was built with a successful company. It's not a startup in a sense, because it's done by a large company as Bruker, which is a world leader of NMR, MRI, with Alcimec Alcon in France, a large company working in nuclear domain, AG in Italy, what is working on a superconducting magnet for high energy physics for CERN, ITER, W7X, and IDOM in Spain, 4,000 engineers in system engineering and research instrument for RF cavity and so on. And we have, cannot reinvent the wheel, we have all the collaboration with a big institute, obviously CERN, NEA, IPP, Max Planck Institute, KIT, and so on, you can see. And now we are defining, I will push faster, we are in the first phase, finishing this year, a CDR, Conception Design Report, when we have to define what we want to do and to select. We select to go stellarator, we select our magnet system. We select our tritium breeding system, and now we'll start next year 7 years of seven years of system engineering to prepare the things to be able in 7 years, 33 to start the pre-construction and to have something in 2040, 2045. We have a lot of competitors that think they can do that in 5 years. Welcome, good luck. I know with a large project need time, but 20 years is challenging, but I'm thinking it's feasible. We have all the partner, money, investor, and all the big company to do that. And I will finish that, okay, I have no time, but explaining that fusion is important. I think we have not excluding renewable, what we call renewable, there was a discussion before. I consider fusion renewable due to the things. But solar and wind is very important if we have to continue to invest, but there is some problem of intermittence, and we have to have a base load if we want to do that and stabilize our electrical network, and fusion will be the base load. And I think now we have a tremendous progress. I think we have to have European project with the main partner to do that. I want just to show you this, because everybody discussed with me that. This is the result of today's, was published 2 days ago, is West Tokamak in Cadarache, not ITER, but this CES things, and they kept the plasma during 22 minutes. It's a low temperature plasma, only 50 millions. We have to go to 100, 150 million, but it was a record above 20. It was a goal to be above 20 minutes. Now they want to go above 1 hour, and I think to keep forever after that. But I think this is already a fantastic result. You can see inside the tokamak with tungsten. Okay, just one slide to say that there is a potential for fusion if we have fusion electricity to produce green hydrogen. And I think also, as I said, there is definitely fertilization between fusion research and hydrogen fusion, because we are using, especially with the tritium isotope, and we can have technology we can use. Okay, and I will stop. I think I like that. Lev, yes, he said that fusion will be ready when society needs it, then when we will be able to inject enough money. I'm convinced we can do that in the next 20 years. And I think the time is now. Thank you very much.
Thank you very much, Freddy, for this interesting talk. And I was somewhat encouraged when I saw the kind of project planning like we know it for big particle accelerator projects. And maybe we are getting some realism into this. So.
Thank you for the very nice summary. You gave a very convincing pitch for the stellarator, and you had a very pessimistic view of the laser confinement approach. And yet
pessimistic on the time.
Yes, okay. And yet there are companies like Marvel Fusion in Munich. So what is your opinion? Why are they putting private money into this?
I think people are putting private money in initial confinement because it's a development of laser. I know some companies, you know Trump, we are discussing with Trump in Germany. They can see if they have attracting private money to develop their lasers, they are very happy. But already discussing with politicians, discussing with a lot of people, some people, we know that initial fusion is far. It always is difficult. We say magnetic confinement of 20 years, but at least 100 years. I said to produce this 1 million of small ball, deuterium, tritium, to provide at 10 Hertz to align all your things, nobody believes that. But it's true, you have Marvel Fusion, you have Focus Fusion, you have a lot of companies. They believe they are selling, they can do that in the next 10 years, 20 years. Okay, we will see.
But you know,
I like when we have research everywhere, but if you have to put some money, I will not put in initial fusion.
But you know, what they call break-even is break-even for the power deposited in the target, and that is 4 orders of magnitude away from the power that is needed to really have break-even. So, and we talked with Omar Hurricane, they are not doing it as an energy source. These are explosions.
If you are doing once, it's okay, but if you have to do
explosions.
I have a more chemical question. You have a lot of problems to solve, you know, but one chemical question mark I had. I have been working with liquid lithium and I have evaporated lithium, and it's very, 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 very aggressive. So if you put your entire system under a vapor of 6 lithium, which you have to do, so with the corrosion, is this manageable?
First of all, there is two ways. There is some company working with this blanket with liquid lithium. We decide not to go to this liquid lithium, to go this in solid lithium. There is a zoo of research on this tritium breeding module. You can do with helium cooling, you can do with water cooling, you can do with liquid lithium, you can do with pebble bed and so on. We start to do with pebble bed, but it's definitely this is an issue. We are doing tests. KIT, Karlsruhe Institute, is the leader in Germany. We have people in CA in France. We have a lot of institutes looking at that, but now we have to pass to industrialization. I don't deny there is a lot of technological problem, but if you are not starting to do that and to do that, I think now it's time, as I said, there is a zoo of different solutions, and I can see new university inventing new solutions. What we decide to do is to take the dominant concept, what is a higher TRL, and to go to industry to do that. We got, in December, a grant of 10 million from the BMBF to look at this tritium. And we discussed, I was in France last week, and CEA, France, and so on, want to put the same kind of money to look at that. We have to industrialize the thing and to look at all these problems. Yes, it's not done.
Maybe just 2 more, and then we have to cut that discussion.
Yeah, thank you for this comprehensive overview and also for sharing the Gauss fusion roadmap. I was wondering why there was no mentioning of the materials issue. First wall, things like that. Why is this not part of the Gauss fusion roadmap?
It is, but I have only 25 minutes, I use 30 minutes. I can spend, but definitely materials, I didn't speak of heating of plasma. Heating of plasma in material is a second level. Materials, we have already some Eurofair 97, grade 91. We know this material will withstand 2, 3, 4 years. We have to improve that. But we can start a fusion power plant with these materials and to remove later and to improve. And I was in Saarbrücken 2 months ago with Saarschmittal. They are producing this Eurofair. They have to improve the purity of the Eurofair. You are fully right. Material is a huge thing. But for me, it's not a showstopper for timing. We have to improve the thing, it's not a showstopper. Heating of the plasma is other things. But we can develop. Only thing for me could be the showstopper is the tritium production. If we are not solving that, it could, if you have not enough tritium to start, and if you are not able to have a TBR, tritium breeding ratio above 1, forget fusion.
So just to summarize, the realization or the risk in realizing too late the Donnes IFMIF facility is not a showstopper for your timeline?
No. It will be better to have IFMIF Donnes. It will be better if we would have a volumetric neutron source. We are looking different solutions. KIT has a project. We have Liberty in UK, there is thing. But IFMIF Donnes will be fantastic to have. It will speed up the process. But we have what we have already developed for ITER, for JET and so on, we can start.
He was first. Sorry, I have to. Stocker.
Your project essentially is a commercialization of fusion energy, which is fine. I was wondering, we know that ITER is a huge project in terms of physical dimensions. Wendelstein is a large project in terms of physical dimension. If you want to sell, I don't know, 100 plants to the world, how big is your plant that you sell? Can you give us some impression of the size of what we're talking about?
Our stellator will be big, 56 meters of diameter. Because if you need to have this 1 gigawatt electrical, 3 gigawatt thermal, you need the plasma. As I said, 2 megawatt per cubic meter. If you want to be 3 gigawatt, you need 1,500 cubical meter of plasma. I asked because I said, why not to build as a SMR or 200 megawatt things? When you are looking at in terms of reduction, in terms of cost, you're reducing by 20%. Then fusion will be bigger. Sorry, will be bigger. Then now it's 56 meter and so on, but it will be 3 gigawatt thermal. We can use this thermal energy, or 1 gigawatt electrical with this Carnot things and so on. But it will be big. But when you are looking at the global fusion power plant, it will not be bigger than a fission power plant.
So I'm really sorry we have to cut that discussion because there are many facets that we hopefully can still over dinner tonight discuss or dedicate a whole symposium to it. So let's thank Freddy once more very much. And now we shift gears again and we go to electrochemical energy storage. And our speaker is Professor Maximilian Fichtner. He is a chemist and he is right now the director of the Helmholtz Institute in Ulm for electrochemical energy storage and also a professor of condensed matter physics at the University of Ulm. Let me see, I have somewhere on this piece of paper his, yeah, okay. He studied chemistry actually at the Universität Karlsruhe and finished this with a doctoral degree in chemistry and surface science in 1992. He then started a junior research group at the Forschungszentrum Karlsruhe, or I think at that point it was still called the Kernforschungszentrum Karlsruhe. In 1994, he then for a time shifted gears and was assistant to the lab management for basic research and new technologies. In 1997, he became responsible to build a new research activity on chemical and thermal microprocessing techniques. In 2000, he headed the group at the new Institute for Nanotechnology at the Forschungszentrum in Karlsruhe. And finally, in 2012, he moved to Ulm as a professor at the University of Ulm, and more or less at the same time, the Helmholtz Institute in Ulm was founded as an offspring of the KIT. Since 2015, he is managing director, and also he is leading several other big-scale research initiatives. For instance, he in 2018 became scientific director of the Celeste platform for electrochemical storage. He is coordinating an excellence cluster between the University of Ulm and KIT for battery research. He has a very large number of publications, 450 plus, but also 20 patents that show that the research he does is really leading to applications. And I should mention last year he obtained the Wissenschaftspreis of the city of Ulm. So now we are looking forward to your talk.
Yeah, thank you very much for this kind introduction. It's a pleasure and an honor to be here. I hear a little bit feedback. This is okay, that's fine. Okay, yeah, what I should maybe mention that in all these different steps, I was working for 12 years in hydrogen. At that time, when I was at the Institute of Nanotechnology, I was representative of Germany in the hydrogen implementation agreement. And and then eventually moved to electrochemical energy storage. And today I would like to give an overview on some of these topics. So some of the things we heard already this morning, and I think everybody is probably agreeing that renewable energy or the renewable energy sources need an interim storage in various categories, so portable, stationary, and mobile. And today, I would like to focus a little bit on the mobile applications. And if we are thinking about future mobility beyond the post-fossil age, I would say, we need to answer a couple of questions. One question is, for example, what is the potential of this new technology to reduce greenhouse gas emissions over lifetime of this technology in an entire fleet of cars? Yeah? And if you do so, the people who are concerned with such questions, they do a life cycle analysis, so they make an assessment of every step in the lifetime of such a technology, from the mining of the raw materials until the end storage or the recycling. Yeah. And this is done here for a couple of different drivetrains. Here on the left we have cars with combustion engines. Here we have electric cars. Yeah? And here you see at the bottom there's such a gray bar. This is the CO2 that is produced during for making the chassis of the car. So you need steel, you need aluminum, etc. And then we have here in the battery, for the battery electric vehicles, we have here a yellow bar. This is the CO2 which comes from the production of the battery itself. For the fuel cell cars here on the right, we have a red bar, which is actually quite similar in size. That comes from the hydrogen storage tanks mainly, because they are very thick structures consisting of carbon fibers and resin, which is baked with the fibers, and they cannot be recycled. Yeah, that makes a major contribution. Yeah, and then we have for each technology here, we have two cases. I would say this is the ideal case where we have 100% renewable electricity, which we use for driving, but this is not the situation now. At the moment, we still have some fossils in our electricity mix, and this is the reason why this bar here is higher. We have a similar situation here for the hydrogen, but this bar is much higher, and unfortunately, this is the situation as of today. And this comes simply because the hydrogen that we use, 99.6% of the hydrogen that is used in Germany is made from fossil sources. So by methane steam reforming, you get hydrogen and CO2, and this gives you a footprint which is somewhere between a plug-in and a diesel car. So at the moment, this is not helping, I would say. But there's, of course, a chance here to get down, and this is when we use green hydrogen. So this actually shows a little bit also the importance to really go for green hydrogen. In the battery case, also a lot is going on to go towards that direction. So I just wanted to show this footprint, which is really developing to smaller numbers. From 2020, we are, at least in Europe, numbers which are maybe 1/3 of it, and in the future it will be even smaller. And at the same time, the CO2 in the electricity mix is declining. So this is actually all going into the right direction, I would say. Okay, yeah, we have not spoken about one potential candidate for the future, and these are e-fuels. I mean, I fully agree with everything that was said today, that we definitely need fuel cells. We will need them for airplanes, we will need them for ships, but we should also make us aware about the potential that we here have. And to assess that, the International Energy Agency made a study recently and collected all the numbers worldwide of the planned projects. And what they found was that until 2035, and this is a critical date, I would say, about 45 terawatt-hour equivalent per year shall be produced globally. That corresponds to about 1/1000 of the global oil production. So it's not so much, I would say. And if you would collect all these fuels all over the world and bring them to Germany, you would be able to supply the German car fleet by 8%. But then the Austrians would not get any, so this may be a problem. So, and now comes the actual problems. Of these 45 terawatt hours projects, only 1 to 2% are really backed by investments. That means most of these projects are planned somehow, but there's no investor. And that means what we are actually talking about are secured projects which cover about 100,000th of the current oil production. Yeah. So if now a politician comes to you and tells you we just have to decide that we go for e-fuels and then tomorrow we can make our entire car fleet carbon neutral, maybe tell him that there are several errors in that sentence. Yeah. Okay, now let's have a look at the drives. And there's a big difference if you just look at the technology. Yeah? If you compare, for example, a combustion engine and an electric drive. Yeah? We have here from a BMW car, here's from a Tesla motor, this is the power here. And you see here actually the difficulty. This picture really reflects the difficulty of making a heat engine principle working efficiently. Yeah. You need all that. I mean, they did not do that for fun. Yeah. they make it because it's necessary to get most out of this principle. And this is much easier in the case of an electric motor. And also there's a big difference in the number of moving parts. Here we have 1,300 in the entire drivetrain. Here it's about 40. Okay, and then let's have a closer look at the electric drive. So we have, as we have heard it already, we have basically two different types. We have the battery electric drive, where we have maybe sun or wind. We generate electricity. This is directly stored on board and drives the wheel. And then we have the electricity which is produced on board of the vehicle. This is done by the fuel cell. And as you have just seen, this needs an entire technology chain. Maybe there's white hydrogen in the future, and everything is simplified, who knows? But at the moment, this is how hydrogen is made and distributed. And each of these steps is associated with an efficiency loss between 10 and 50%. So eventually, this multiplies to an efficiency which is pretty close to what Ingo Krossing calculated, in the order of 18 to 20%. It's less if you use liquid hydrogen, because the liquefaction eats another 40% of the efficiency. Okay, there has been another calculation done by the German Association of Electrical Engineers, VDE. They did a Gedankenexperiment, if you will. They said, okay, let's imagine we have a windmill, and we would like to see what we can do with the electricity coming from this windmill. How many cars can we supply? Electric cars, hydrogen cars, and cars running on e-fuels. And this is what came out. So by electricity, you have 1,600 cars, 600 cars running on hydrogen, and about 250 cars running on e-fuels. Okay. Now, as I said, I'm also coming from the hydrogen field, and if you would have asked me maybe 2 years ago, where will we see the hydrogen in the mobility, I would have probably said trucks. Yeah. Because hydrogen contains a lot of energy, you can charge it relatively fast, so maybe trucks. But let's have a look. Also here we run in one big problem, and this problem is cost, as we will see. If you ask consulting companies like P3 Automotive, which is the biggest worldwide, they tell you that hydrogen for heavy duty gets competitive if it's getting cheaper than 4 to 5 euros per kilogram. Yeah. Currently, in Germany, you pay between 16 and 18. That means, and this is gray hydrogen, as we have seen, gray hydrogen. In Austria, it's even more, 24 euros per kilogram. In Germany, the hydrogen is not taxed as a fuel. In Austria it is. This is why it's more expensive. That means you have to get this cost down by a factor of 4 to 5. And this is difficult for the green hydrogen in particular, because there the costs will be even higher. At the same time, the costs of the batteries are constantly declining. And then I would say what kills the entire story is the driving times of a diesel, of a fuel cell truck, and of a BEV truck are identical. How comes that? In Europe, a truck driver can drive for 4.5 hours, then he must make a rest for an hour. And the companies which already run BEV trucks, they just get to the next station at the Autobahn, plug a regular fast charger in, and load enough electricity for the next 4.5 hours. And they say they can never run their truck empty. So it is true that you can supply your car faster, you can fill it faster with hydrogen, but that doesn't matter in that case, because you have to wait 1 hour anyhow. Yeah, and then if you calculate the cost, I tried to do that for diesel. There's a wide variation in the consumption, so I came to something between 40 and 50 euro cents per kilometers. For hydrogen fuel cell trucks, I took the number of Nikola. They claim they consume 8 kilograms per 100 kilometers. That makes €40 in Germany. Yeah. And then if you look what a BEV truck consumes, this is according to a test from ADAC of a Daimler e-Actros, something between 35 and 55 cents. So now the diesel is slowly fading out, by law, I would say. So a transportation company has to decide between these two options. And I can tell you one thing, a transportation company decides on basis of the investment costs, but even more on the kilometer costs. Because their trucks, they run for more than 1 million kilometers. And this is actually reflected in the actual registration numbers. This is worldwide. There are fuel cell trucks. These are the green ones here on top. And the rest here are battery electric trucks. In Germany, last year, for one fuel cell truck, there were 500 battery electric trucks that were registered. Okay, so obviously there are some challenges, and we heard already in the second talk this morning that hydrogen has a cost issue. And this is exactly what we've seen now. And if we want to do something about that, and we want to get the costs down by a factor of 4 to 5, there are a couple of things that are ultimately necessary. We need to reduce electrolyzer cost. We need to reduce the electricity cost so that you get it virtually for free. We need to increase the electrolyzer efficiency, so there's a lot to do for Beatrice, I think, obviously. And if we do that, we can maybe get the costs down by a factor of 4. If not, if just there's no way to lower the electrolyzer costs, this will be only a fraction. And then came out a recent work from Harvard Kennedy School, where they investigated carbon abatement costs of green hydrogen across end-use sectors. It was published in Joule, and they say distribution of hydrogen is costly. Point. Even if production costs decrease in line with the prediction, what we saw in the previous slide, storage and distribution costs will prevent hydrogen being cost competitive in many sectors. And they claim that this result actually challenges the idea that the hydrogen will be kind of a Swiss Army knife for decarbonization, and they suggest that the opportunities for hydrogen may be narrower than previously thought. They will be there, I think this is for sure, absolutely, yeah. But the options will be maybe not as many. Okay, then let's have a look at electric cars, what has happened. And also there we have a cost issue. Yeah? We have a cost issue, and what we have here is a cost curve which looks pretty much different from that what we know from the hydrogen case. Yeah? This is actually a predicted cost curve which came out to be real, that was calculated originally for cars with 350 and 400 kilometers range about 10 years ago. And at that time, there was basically only one car which could deliver this huge driving range of 350 kilometers. And then 5 years later came Tesla Model 3 for 50% of the cost. Yeah. And now, as we know, Chinese have gained ground and come out with cheaper and cheaper cars, and this is a model which came out last year from BYD, running on an LFP battery. So it's a battery with no cobalt, no nickel inside. It's just iron-based on the cathode. Has 400 kilometers range, costs 14,000 euros. Yeah. And if we go even further, we see that we are slowly reaching the target for stationary storage, really large stationary storage in electrochemical form. Okay, that this is not just a prediction. Is, I found in the internet this advertisement of cars. There are two Chinese manufacturers, BYD and Changan. Hyundai is Korean, yeah, and these are the costs, yeah, and if you translate that, somewhere around 10,000 euros. If you buy a hydrogen car, Hyundai Nexo, for example, it costs you about 80,000, and it costs in the production, it costs 120,000. So this is not really great for making money. Yeah. And in fact, in China, since last year, about 2/3 of the electric cars are already cheaper than the corresponding models with combustion engines. Yeah. And this has been has had an impact. Yeah, these developments. This is the lead market, China. You see how the number of combustion engine vehicles is declining in the sales. At the same time, the cars with a plug are inclining, and you had a crossing point in July last year, and now as we are curious scientists, we want to extrapolate that. It seems to be quite linear, and that would mean, if this trend persists, that in 2028, only 5% of the sales will remain combustion engine cars. In Germany, we have this discussion that some people say, let's stay with our proven technology. We have always been world leading in combustion engines. We are crazy to give that up. I'm pretty sure if we keep on just doing the same things, we will maybe remain world leader in combustion engine cars, but in a shrinking niche. Yeah. And this is something which should be clear. Yeah, Europe seems to react, as it seems. These are just a collection of models which you can buy already under 30,000. And then there's also one thing that is bothering a lot of people, is the range anxiety. So they fear that the car is not running far enough. And these are all models now with more than 650 kilometers. Driving range, not for 30,000, but a bit more. Okay. Now, in all these cars, we have lithium-ion batteries. And why did in particular did the lithium-ion battery make it? Yeah? Why has it been so successful? This is a quite old graph here, 2015, but it shows nicely what actually happened. Since the market introduction, 1991, the energy density went up by a factor of 4. At the same time, the costs decreased by a factor of 50. There is no other technology no other technology which would be comparable. And alone in the last 10 years, there has been a 90% cost reduction, and the energy capacity doubled to tripled in the same period. And all that was possible, actually, because we had a quite fruitful interplay between chemists and engineers in that field. I'll give you some examples. One example is that the community has relatively early started to look at critical raw materials and tried to get them out of the battery. And one example has been cobalt. What you see here is actually the amount of cobalt, the cobalt content in the positive electrode of the batteries, which was gradually replaced by nickel and manganese. So this has been the original structure, and the cobalt was, by keeping the same layered structure, was replaced by nickel and manganese. And then now completely different types of storage materials have come out, like these spinels or these olivine structures, the lithium iron phosphate, all these materials that do not contain a single milligram of cobalt. So it's also materials transition, Materialdämmerung, as we would say in German. Okay, at the negative electrode, something similar is going on. So originally we had petrol coke as an anode, and then this was gradually replaced by natural graphite, synthetic graphite, and now comes a mixture, a composite, consisting of silicon and carbon, which has 4 to 5 times the capacity of the natural graphite, and on a cell level, this boosts you the capacity by another 40%. And then on the next level, we have the battery cell, and also there we have new battery cell designs. So there has been, over the years, there had been a gradual increase here, year by year, where the capacity climbed up. That was mainly achieved by improvement of the materials. And then you would expect, okay, maybe there's a certain saturation or something, or maybe it will go further. But what actually happens is that here. And this is very interesting, because there was a complete new view on the battery cell. So people found that actually parts of the battery cell, where you would say this structure has been carved in stone, these parts are actually not necessary to run the battery. You can leave out the carbon, for example, in the anode, and you can deposit the lithium directly on the current collector. So this saves you a lot of space, and it saves you a lot of weight. And these are called zero excess cells or anode-free cells. So the first examples here are already under development by startup companies. And if this would come, really, I don't know whether it comes, but if this would really come and make it into application, we would have cars running for 1,900 kilometers in the range. Or you have batteries which are just half the size. The next aggregation level is the battery pack. And here we have a picture of a European battery pack. So you see here these light blue structures. These are the battery cells. So these are prismatic cells, maybe of that size. You put 12 of them in a box, a little bit bigger than a shoebox. You call that a module, and then you take these modules and put them in an outer container, wire everything, and then you have your battery pack. It works well. The disadvantage is you have an enormously high fraction of packaging material. All these containers, all these wires, etc., lead to a device which contains only 25% of storage material. The rest is packaging. Now, the Chinese came a couple of years ago and said, okay, our production facilities, our knowledge is so far developed that we can also dare to make large cells, which are still perfect. Maybe of that size, like a board. And this is the so-called cell-to-pack technology. So they build cells which they integrate directly into the pack. There's no wiring, they just click it in, finished. Save 40% of the number of parts that is needed to manufacture the pack. And this gives you new opportunities, gives you new driving ranges, and opens up opportunities for lightweight materials, which have not been taken into account because they were too fluffy, like the iron phosphate. And it comes now. This is, in reality, such a battery, and since 2032, you can buy that. It gives you more than 1,000 kilometers driving range. It's the first car that has been running around such a battery based on iron phosphate from Geely. It's the mother of Volvo, Polestar, Link, etc. Yeah, and there are other developments, and they go in a little bit different direction. They go the direction of faster charging. I think this is maybe the even more important direction to go. I don't know whether we really need 1,000 kilometers driving range, but we need to charge up fast. Yeah? And this is a car running on a Shengxing battery by CATL. This enables you to charge 400 kilometers driving range in 10 minutes, 700 kilometers range. This is a charging rate of what we call 4C, so 4 times per hour. And now there has been a follow-up. It's just been released in fall. This has a 6C charging rate. So you can charge between 10 and 80% in 8.5 minutes. This has been proven. Yeah. But you need the right charger. So this is the next thing. So what you can do is actually charge about 1 kilometer driving range in 1 second. And this is the last slide. This is about durability and safety. Yeah. This is a car which has just been released where they claim that the battery runs for 1 million kilometers without any degradation. Yeah. So there's no decline of the capacity or anything else, and they give you a guarantee for that. They have an in-house produced short blade battery, and this is not only running for a long time, it's also very safe. And they have developed a dedicated safety test procedure, which they call the 6 tortures. This is like in a Chinese restaurant. You always have an item which is called the 7 delicacies of the emperor or something. And here they have developed the 6 tortures. What they do, for example, they make nail penetration tests here. Typically, such a battery cell would go up in flames because you have an internal shortcut. Here, there's only 60 degrees warming up here at this nearer zone. So they bend the cells, nothing happens. They let them drop from a high altitude, nothing happens. They throw them in hot water, nothing happens. So they are pretty much safe. Okay, now I come to the conclusion. I think for the implementation of a hydrogen economy, we have some major issues. One is the fact that the costs are too high. We've heard that today already. And then the fact that the hydrogen is everything else but green at the moment. But we need green hydrogen, or maybe white hydrogen, whatever. We need that. And then also supplying infrastructure is still something to be done. From the greenhouse gas emission aspect, the battery vehicles have the lowest emissions, they have the best energy efficiency, and the lowest total costs of ownership, I would write here. So there's a mega trend towards moving away from critical raw materials because we want to build a world fleet of cars, and to reduce manufacturing costs. In chemistry, I showed you a few examples what is going on. I see some prospects in the anode in particular, and what I didn't talk about was the new chemistries like sodium-ion batteries, but they are already there, and they will probably find their share in the market. Yeah. From the engineering aspect, we have these new designs for the packs. which allow us very long driving ranges. So 1,000 kilometers is now standard, at least from the Chinese manufacturers, 700 kilometers charging in 10 minutes. And if we really take the latest results from the research and take that for granted, and this can be transferred in an application, then we would achieve 1,900 kilometers driving range with a single charge and a charging of 1 kilometer per second. Thank you very much.
Thank you very much for giving us this rather comprehensive picture and putting together all the information. So I see the first question here, and then since I skipped Katharina,
so
she's
with
next.
respect to the engineering aspects, you mentioned faster charging and so, but we have also to keep in mind the limited resources. What about recyclability?
Yeah. I think at the moment we do not have really limited resources. I mean, there were some concerns about lithium some years ago, but meanwhile there have been so many places found where lithium can be mined that this is at least shifted to some later time. Yeah. The next is there is a European regulation that batteries must be recycled. Yeah. And what you get is a battery passport on each battery, which shows where the materials come from, what is inside, so that you can make a good separation of the different types of materials. And they have an increasing fraction of metals that must be recovered in the next years. It's going up to 95% or so.
So then, Katharina.
Yeah, thank you for the interesting comparisons. There's one aspect which could also speak pro-battery, which is if you have bidirectional charging. Now, let's say for me, I have a 10 kilowatt hours battery pack in my for my solar roof, but I have a Tesla with 90 kilowatt hours in front of my house, but I can't use it as a battery for the house, for the solar surplus or so.
Yeah, in fact, this has saved lives in one of the winter storms in the United States.
Yeah. So how many of the cars are actually bidirectional now?
Absolutely. If you have a car in the garage which has a 70 kilowatt hour battery, this lets you run your house for a week. Then okay. Yeah. The answer is the European regulations allow bidirectional charging, but in Germany it's not possible. And this is maybe, I think the Finanzamt has something to say here, because in principle you could charge your battery, you could charge your car in the job for free, and then you bring it home and then you supply your home. And this is not, this would not be taxed. So
there are many ways to steal.
Yeah.
Thank you very much for this interesting presentation, and your comparison definitely made strong arguments for an all-electric mobility of the future. However, I would like to stress a little bit the infrastructure issue, which you didn't really talk about, at least in depth. You mentioned that it's very difficult for hydrogen. I would make different arguments than you, but yes, it's difficult. But you did not talk about the electrical grid, to all of our homes, which is probably an issue. And you didn't talk about, say, the infrastructure issue from the perspective of densely populated regions with older buildings where you have hardly the space to charge the cars. So what about the infrastructure consideration in all these assessments?
Very good question. I think your last point is the most important one, is the most critical one. We are lacking of chargers, not only for electricity, but also for hydrogen in densely populated areas. I think it was Ingo Krossing who mentioned that we need, if we would take our 48 million cars and would run them entirely electric, we would need another 25% electricity. At the same time, we would save 500-something terawatt hours per year fossil fuels. Yeah? So we would need another 125 terawatt hours electricity, and we would save 500. So, but this is only the overall picture. In reality, we need more Mittelspannung grid. Yeah? So grid between 10 and 30 kilovolts. This is clear. And what helps us for the trucks, for example, is that the high voltage lines are typically running along the Autobahn. Yeah. If you think of a hydrogen world, I can tell you the following. An average gas station in Germany has about 300 fillings per day. So one delivery truck for hydrogen, and now we come to the distribution, brings about 300 to 500 kilograms. That means you need 5 delivery trucks per day to supply the filling station. And if you have a filling station for hydrogen for trucks, yeah, one tank filling of a truck is 80 kilograms. That means you would have to have for each filling station one delivery truck plus driver, which is doing nothing else than bringing hydrogen all the time. Yeah. I would like to see the costs of that.
Maybe I have to cut this question and one last question in order not to put our final speaker under too much pressure.
That was a very excellent overview. I just missed some words about sodium. So recently there has been some interesting material science, and given the abundance of sodium, that is certainly worth being mentioned.
To make it short, the first sodium batteries are already in cars. Yeah. Sodium has the advantage that it migrates faster, not because it's bigger, but it has a smaller solvent shell. Yeah? So the hydrodynamic diameter is smaller. So, and it can be stripped off more easily at the interface to the storage material. This is why everything goes faster. And especially at low temperatures, you can still charge the battery very fast. And you get 90% back of your energy, while in a lithium-ion battery, it's maybe 70%. So you're better than a combustion engine car in that case. So there are advantages. The disadvantage is the lower capacity.
Okay, so let's thank Maximilian Fichtner and come to our final speaker.
Yeah, I have the pleasure of announcing our final speaker, and as the saying goes, he is truly one of those who need no introduction, so I will keep it short. Robert Schlögl studied chemistry and got his PhD at the Ludwig-Maximilians University in Munich in 1982, did a postdoc in Cambridge and in Basel, carried out his habilitation with Professor Robert Ertl, Nobel laureate, at the Fritz Haber Institute. Immediately after, he accepted a call to Frankfurt in the inorganic chemistry department, and was in 1994 appointed to his current position as the director of the Fritz Haber Institute of the Max Planck Society in Berlin. Also, because he had probably not already enough to do, he was appointed in 2011 as the founding director of the newly minted Max Planck Institute for Chemical Energy Conversion in Mülheim an der Ruhr. He has received numerous awards, honorary doctorates, honorary professorships. I'm not going to name any of those because we'd be standing here for hours. I'd much rather have him speak about hydrogen and the energy transition. Robert.
All right. Good evening. First I have to thank, of course, the organizers to put me between the dinner and where we are now. That's very bad. Secondly, of course, you will see that I have to switch gears again, because after these 15 brilliant talks we heard today, it's very difficult to add a 16th one with a little detail. So what I'm trying to do now is to bring you in a helicopter and look from a far distance on the global aspect of the whole thing. And one remark that I want to make here is much of the discussion that we have heard before is very Germanocentric. So we think energy transition is a German problem. And the conditions that we have in Germany or possibly in California, they are applicable to everywhere in the world. And I want to remind us that this is grossly wrong. Most of the world is neither of the two. And that is the reason why possibly some of these discussions, they apply to regional discussions that we'd like to have here in our government, but they do not apply to the global problem, and I want to focus on this. Before I do this, unfortunately, I have also to focus on that, because we are all sitting here and discussing the future of the world and forget about there's this problem of external security. And there are some people in the world who die at the very moment where we are discussing this. And the last days that we have heard, they show us very clearly that the world has forgotten that these people are dying for us, and so we should pay them some tribute. So, sorry that I have to say this, because we shouldn't be in a position that we have to talk about such things. So, global dimensions. I begin with what is the amount of global energy that we use, and this is this diagram here. And when you look at it, first you look at the y-axis and you see 180,000 terawatt hours a year. That is a pretty big number. This is equivalent to some 50,000 nuclear power stations. Okay? This is what we're talking about. And then we see, when we look at the colors, only the light blue part is renewable energy. Okay? And only the dark red part is nuclear energy, and the rest of it is dark blue water, and the big colors is all fossil. And who believes of you in 25 years all this is gone? Certainly not me. So we should also learn on a global scale this idea about Paris Agreement and in 25 years everything is fine and zero emission. No. That's not right. This is the first thing to begin with. Simply the dimensions would never allow this. Imagine how many plants and power lines and whatever you would have to build in order simply to replace all the fossil energy that is here. But what's good is the rate of defossilization is faster than the rate of fossil energy growth. Okay, that is a very small precondition of what we are starting with. Here you see the numbers. So, and renewable energy is 15,000 terawatt hours in the world. Okay? I think this sobers us a little bit. How much have we achieved so far, and where do we have to go? I can now do this from the other side and look at the CO2 emissions as a function of time. And it's another 50 years, so that you see also the graph here. And the dashed lines have the same slope in here. And then you see very clearly, okay, they should correlate, because we do believe that one is the consequence of the other. I will show you it's not that easy. And the bad part is at the very end, you see there's a discrepancy. And this discrepancy is what we have saved in CO2 emission over in the world. Okay? Everything that we have done, every nation in the world with all the renewable energy and every energy transition has just achieved this. Again, that tells us how realistic is everything that these politicians are discussing at the moment. The rate of CO2 reduction in the world was halved by the increase in the emission of cement production. Okay? That also tells you something. So again, before we discuss any of these details that we heard so beautifully here, we have to really think, what is our task? And the task is remove the CO2. There's a correlation that shows you in red the emission of CO2 in our planetary atmosphere, and you see enormously bad. It's an exponential curve. And what you also see in blue is the amount of CO2 emission that we have. And you see, there's some correlation, but it's definitely not an agreement. And what you also see after the year 2010, this gap becomes bigger. Why is this? because we see now the planetary emission sources of CO2 that have nothing to do with us. Because we are going to lose control over our experiment. We have initiated planetary processes that are much more powerful than the emission that we do. Okay? You should also think about this. We can go a little bit further in numbers, and then we see what kind of amounts of CO2 do we have to remove. Yeah, we see 10,000 million tons. Okay, yeah, it's a task. So Germany is not such a big problem. There you also see, it's a 2% problem. But, and that is a very important message, Germany, of course, is not important for the global climate, but Germany is pretty important as a role model, what people should do or should not do. And I dare to say, without definition, at the moment we are a role model what we should not do. You can see this here, again, the trend line. This time I put this on a logarithmic scale because then you see the trends better. And you see there are 3 trends. There are 2 nations in this planet that grow, where the CO2 emission grows enormously. You can imagine who that is. This is the blue one, this is China, and the black one, that is India. And then you can see a line that is horizontal. That's the yellow line. This is the US. And then you see this little red line, and this is us. Okay, and one sees very clearly the differences here on a long time scale. And you see also the historic record that we have in removing in 25 years all CO2 emission is extremely unlikely. Just to support what I said in my first slide. Renewable energy is necessary, yes, of course, that is the replacement. You have heard this before. Again, you see the hit list. We think we have done a lot here, but look what are the numbers in China. And what I calculated from here is, on the other slide, is how many years do we need to implement 100 terawatt hours of renewable energy capacity? How speedy are we? That's interesting. China, half a year. That is really growing. They are doing something. Germany, 10 years. Spain, 23 years. That's not the worst. There are countries that are much worse than this. But it tells us again, we are talking a lot. So there's a lot of lip talking here. And there's not so much doing. And in particular in Europe, we should be very careful talking other nations what they have to do. Maybe they do it here. This is our CO2 profile. Where does the CO2 come from? And we are here now. We see electricity is not so much our problem anymore. We have done a lot on this already. Only in Germany is a problem. Half of this is German electricity. Then, of course, we have industrial processes, no change. That is buildings, heating. That's mobility, what we had before from Mr. Fichtner. This is the biggest single contribution in Europe. That's very different in different parts of the world, but here it is. And then, of course, this is minor things. I have no time to go into that. The trend that we see is, yes, energy is going down in Europe, but to a large extent, this is not because we are so good in doing our renewable energy. But the largest contribution of that is that we have outsourced our industry to China, and so this emission is now in China. That hasn't saved much to the global climate. And that's what we are heading for. So that was the 1.5 degree target with negative emissions and all these beautiful dreams. Gone. That's the 2 degree target, also gone. So very likely no chance. That is what people promise. This is what we do at the moment, and that is if we don't do anything, if we stay with our lip service. And what we see at the moment politically is very likely that we will end somewhere here. That is the projected probability. Now, this is not so much of a problem only because we have a continuous change of our planetary conditions, but when you look at this and project it into the future, CO2 emission will in a long time not go to zero. It's also not necessary because we know from climate science that it takes about 10,000 years that the CO2 disappears again from natural cycles. Because the CO2 is not assimilated by biology or by the land. The CO2 is assimilated essentially by the deep ocean. And the transport times are many thousand years for that. And for that reason, you can also forget about climate neutrality in 50 years. It's useless. You don't need this because the CO2 stays here for thousands of years. And the maximum of climate heating because of CO2 will be likely in 2,500 years from now, not now, because of these transport processes in the ocean. We are careful about this. So the solution is also clear. We have heard this many times before, and what we do at the moment is this, what Beatrice, I think, called this the physical part of renewable energy. This is photovoltaics, brings electrons, it combines it to power stations. We have battery storage. Yes, we will need this very clearly. And of course, we have thermal storage, and we have fusion, and certainly fission, I think, is not a very good solution, but fusion is a solution, and we should certainly work as hard as we can on this. And then, of course, is the white part. This is what we're talking about, it's the hydrogen part. The hydrogen part, unfortunately, is a little bit more complicated. I have, unfortunately, no time to go into all details, but I have certain elements that are important. So PV and wind will certainly not be used on the global scale in parallel on the grid. That is useless. You just take this off-grid as an insulation. You build your PV stations and your windmills only to make hydrogen, because only then you get really the advantages of large production and cheap prices. You need water for that. That's a problem that we also have to solve. This is solvable, but it is a problem, in particular in many important areas in the world. Then you get your hydrogen. Then comes this storage and derivative issue that we have discussed before. And one point that is always forgotten, we need always this. That's absolutely necessary. And of course, that was said, we need always some e-fuels. The debate how much of this is a different question. And I agree certainly with the previous speaker, we should not use e-fuels in order to drive to the bakery in order to get our breakfast next morning. That is not a good application. Certainly true. Now, there is lots of details on that slide, but I have no time to go into that. Just mention you one. Why would we use other things than hydrogen? One very good reason is when you go to global dimensions, this is the density of hydrogen in your energy carrier. And everything that is on that list is much better than hydrogen itself. So ammonia is twice as good. If we think about global dimensions, it makes a difference if there's a factor of 2 of storage density in this. And that's the other reason that we have seen before. This is German power. 6th of November last year. The power price in Germany went to 1,500 euro per megawatt hour, because the weather models were wrong and they didn't project exactly what the amount of renewable energy would have been. That tells us it is always necessary to have an electrical system that has 2 generation parts. And the 2 generation parts, unfortunately, have to have exactly the same size. That's always forgotten. This idea with we shift around the load and there's load management, and this is pretty unrealistic. That works for cars, we have heard this before, but it's a couple of % of a national energy system. In gross dimensions, you need just 2 parallel systems. And I have a question of how big are these systems, how do we use them? That has something to do with pricing. This is in blue the amount of residual load of the German system this year, so it starts January 1st and all the days. And it plus how many % of this is not coming from renewable. This is quite a bit. And you see this enormous noise. This is why I showed it to you in a resolution of 15 minutes. That you see how many gigawatt hours do you have to change in 15 minutes. There's not so many technologies that are that fast. This is extremely critical. Yeah, you don't think this is a problem. This is a very big problem. And what that means is we are absolutely sure if we want to have a stable electrical system, we need these 2 parallel generation parts. And it is not a good idea to say we minimize the conventional one and we maximize the non-conventional one, because on the long run there will be stability problems. We solve our stability problems in Germany at the moment by just importing electricity from France and from other countries. But imagine the other countries would do the same as we do, then we have a problem. Our government has planned for this, and there's this famous Osterpaket, and they have exactly decided what the future of our system will be. This is law, by the way. This is not just a projection. This is what we have to follow. An interesting part is what you see there in red is the batteries, and what in light blue see is the amount of combustion power stations. And the rest of it, enormous gigawatts of renewable energy. Yeah, that is bound to work. Now comes McKinsey and says, oh, if we double the capacity of the production by combustion, what I said is necessary anyway, then we can certainly make the energy system smaller. The consequence is we save on the order of 250 billion, which is no money. No, it's not important. Because that is paid by all of us as sogenannte Netzgebühr. That is these billions. And you see, it's a good idea to think about how we do that. There is some requirements. We have to change our grids in order to do that. But it's interesting that McKinsey also said that what heard in the previous talk, hydrogen, in particular green hydrogen, is too expensive for that at the moment. This is an interesting debate. The power price that is projected from this is exactly the same power price that we have today. So if we build all this according to this model, then we would say the end user price of electricity doesn't change much. This is pretty much what we pay here today in Germany. What was interesting is about how many percentage of the year, how many years, or how many hours in the year will we use our combustion engines, our combustion machines to produce electricity. The sad part is, if you use just normal gas and pay compensation, that's the cheapest version of doing it. So we don't save any CO2, we just pay compensation. This is another thing that tells you how careful we have to be with our legislative groundwork. Because very simply, we just give wrong ideas. What you see is blue hydrogen, yeah, it's okay. And the most expensive one is, of course, take the conventional gas and use CCS. And what we see also very clearly is this goes only to acceptable power prices if you use this about half of the year. And it is not a good idea to minimize the amount of runtime and maximize the amount of batteries. This is very expensive, and this is also very expensive in running it. Now, we have heard hydrogen is a platform molecule, but hydrogen is not the ideal energy derivative. There are others. So I have just put some ideas there. And we have a choice, and it is an important thing for me to say, we should not decide on one of these things. I have the impression that as we have it today, we will have also a distribution of these carriers in the future. Why do we have to decide that this is only one? At the moment, we also use a whole mixture of different energy carriers. There is no need to say this is only one is good. Ammonia is fine, but ammonia is a very bad fuel, so you shouldn't try to burn ammonia. It doesn't work anyway because ammonia doesn't burn. And if you try to do that, then you get a lot of N2O, and this N2O is a very big problem because of enormous greenhouse gas factor. Methanol is fine, but we have heard this before. I'm also a methanol fan, but it has the disadvantage. You have to close the carbon cycle, otherwise it's not true. That is true for all the other organic molecules there, and we can discuss whether ethanol is better than methanol, so that is detailed. So I guess that all of these things will have their applications. Our German industry has made very good planning for that. And what you see there in Germany is that the transformation is machbar. Yeah, we can do this. Provided we have a power cost of 40 euro per megawatt hour, which, okay, that's an interesting target. And they want also 500 terawatt hours in 25 years for their purposes. This is only the German chemical industry. Okay, this is about the whole electricity production that we do at the moment. Then everything is doable, fine. What they discuss at the moment is, of course, the technologies. They have no time to go into that. This takes too long. But I think what we should discuss in a moment, and I know that I have to rush, you want to go for dinner, is the question, how big will our energy system be? There are people who say 500 terawatt hours only for the German chemical industry is economically not useful, just throw out the chemical industry. This is a serious debate, and this is in many political circles, this is indeed said. And just to copy for that, there is no reason to say that energy transition has something to do with making energy systems smaller. No, no. This is a transition, and this is not about saving. And there's this argument we have to save anyway because there are all these poor people in the world who don't get any energy. Be careful with this. This shows you the amount of kilowatt hours that we need in order to generate $1 GDP in different areas of the world. And look where we are. Okay, that's also an argument. This is a very complicated figure to interpret, so don't think this is easy to understand why this has this relation. But what is certainly clear is we are not the biggest wasters of energy on this planet, definitely not. How much hydrogen do we need? This debate we also had today. And I give you here just some numbers. If we want to convert from our world energy consumption that we have at the moment only 10% into hydrogen and its derivatives, then we need to produce about 410 million tons of hydrogen per year. Okay, so 410 million, okay. But it's hydrogen. If you convert this into ammonia, then it becomes more acceptable. It is 3,485 million tons of ammonia, and the world production today is 150 million tons. And you need 3,000 big plants to make 150 million tons. And then it becomes also understandable why I do never think that we will have a complete energy transition in 25 years. You wouldn't even be able to build all these plants that you need for that. One short excursion to some form of hydrogen generation that hasn't been touched upon in the whole meeting so far. Of course, you can use non-sustainable other forms of carbon in order to make this. Frédérick alluded to this. That was extremely useful, and it just provoked me to put this into my presentation. Of course, in energy-wise, it is clear to split water is the most expensive thing that you can do, but this is, of course, the most sustainable one. Or you can also say, if you consider this as a chemical battery, so of course, the storage of energy is the largest one if you do this by water splitting. You can do this, of course, also by steam reforming that we do today, but that is very attractive. So that is good. Pyrolysis is not a bad thing. The bad thing is there is not so much hydrocarbon that we can use for that. And dry reforming of methane is yet another technology that hasn't been touched yet. That is something for specialists. Why is pyrolysis a problem? This has a little bit to do with the temperature that you need to do this with reasonable speed. So this is a classically high temperature process. So German industry is not afraid of this. We had many high temperature processes in our industry. That's not a problem, but it's not cheap. And of course, catalysis helps, as you can see, but the problem is the carbon that you produce does not allow that you recover the catalyst. That means the catalyst stays in the carbon. As long as this is an earth-abundant thing, it's not toxic, you don't care. But nickel, you can't have. Nickel is way too toxic. You wouldn't, only for that reason. And what is also interesting is what do you do with this carbon? This depends, of course, what kind of carbon do you want? You have a menu here. Depending on the conditions, how you do this pyrolysis, you can have all kinds of carbon. So we heard in the previous talk, there is certain cokes, petroleum coke, and there's graphite, there's artificial graphite, and there's many more things to that. And we have full control over that. So yeah, I look at you, you do this all the time. You control these nanocarbons. That is a very useful thing. And this allows us, of course, to think about that pyrolysis is possibly a useful technology in order to generate carbons for applications that we do not think at the moment. Building materials, roads, for improving our soil, not for batteries. This is simply not enough. So you don't need gigatons of material for batteries. A few pictures that you see, there are really different forms of carbon that you can make from different catalysts. The details don't matter. But I want to leave you with this impression there's a wide field of things that is not explored enough in terms of energy. There is more to do about this. 3 minutes? 5, okay. This was a bad decision, so I tried to run. So again, dimensions. This is the largest electrolyzer that exists in Germany at the moment. That's working. And then you see what the balance is. So Beatrice had a similar thing, but this is reality. And you understand with this huge thing, and this is 10 enormous materials, you see the tree size, then you understand how big this plant is. This is at the moment, as I say, in Salzgitter, and you see this makes 2 tons of hydrogen per hour and requires 110 megawatt hours of power. So this is, this is, the densification of energy by electrolysis is enormous, but which is good, because you want to have an energy carrier. But I have to compare this again what we need. So the careful expectations from the International Energy Agency say we need about 600 million tons. So I said we need only 400 million tons because I'm more conservative than they are. But imagine this little thing. You need 60,000 of these plants. That's why I said, who should build this in 20 years? This is an enormous installation that you have here. But hydrogen is a good fuel, and I want to leave you with this impression. This is not just something that is unrealistic. You can really build furnaces, industrial plants where they can heat with hydrogen. Yeah, it's possible, it works. It's very loud, and this is something that we didn't hear yesterday, Frédérick, in your presentation, because the flame was so small. But when you let the real flames burn, then this is enormously loud, because you see at the end here, there's lots of little explosions. This is this part where you see this NOx coming out. This is wherever there's flashes of explosions. So it's very loud, it's not so easy to control. That I skip. That I also skip. No, I leave this. The idea is, I have heard, these renewable energy carriers, they only come in the future. No, they're already there, but you don't see them. The photograph that you see in the center is the Rotterdam port, and these tanks that you see with this gray color, these are ammonia tanks. So we are not talking about the future, that's already there, because in Rotterdam, private companies invest in that, and they have already these big ammonia tanks, and you see there are 2 ammonia ships. And the same private company that has built the tanks in Rotterdam, they are setting up now a tank farm in Duisburg, because they have understood they will never bring the hydrogen with pipeline to Germany. That takes decades to build. So they put this on a ship, and then in 2 years' time, the hydrogen will be in Duisburg. But it's all done by private enterprises. There's no state involved in this. I have to skip this. This was essentially for my previous speaker, but I also skipped that. I come to my end. Climate neutrality is impossible by 2050. And the first thing that you should take from here is we need expectation management. We need to stop telling people that this is being done, because that erodes simply the authority of the state. This is only to tell you 100 megatons of hydrogen we make at the moment, and they celebrate we make 4 million tons with green energy. Yeah, okay. This ties in what you said before. The difference between what is announced and what is being built is so large that we have to speed up enormously to get at least a little bit of this hydrogen that we need. Technology leadership is fine, but no one should be the forerunner in implementation. We should not be the first country in the world to do this, because we will be dead by the time we do that. But we do this all together. Climate club, that's the right answer. We need 3 pillars, and then we are done. Direct renewables from sun and wind, yes, clear, we need that. But we need also to think about the emerging world market for molecular energy carriers. This is not something that we decide in Germany. It has been already decided. We know that this is going to come, and the only reason is, are we buyers or are we technology providers for that? That is at the moment, well, I don't know where we stand there. CO2 price is also very important. We haven't discussed this here, but that is a very important element that we get this thing done. But we should also recognize at the moment it's a punishment, but in the future it's a value. Because if there's no more fossil energy, then of course where does our carbon come from? It will come from CO2, and then it costs something. And we should be very careful what the state has to do, because the state should not manage the energy transition. The state should give a frame, and in the frame, the private companies do what has to be done. Energy must be global. We are going now for dinner. It is not a good idea to think that renewable energy is something that is very valuable. No, it's not. 0.5% of our surface of the planet full with photovoltaic devices solves the problem. 0.5% is not much, no, okay, but the planet is also pretty large. So this is a huge enterprise to do that. But it will be done, it will happen. And it will take less than 25 years, I'm absolutely convinced by that. This is why photovoltaic devices are so cheap. But the point is we have to store and transport this. And if we do not accept that this is an integral part of an energy transition, it will not work. Wrong time, wrong space, that is our problem, not the abundance of energy. That is no problem. I end with this. My wish list for the new government. You can send this. Don't stop energy transition. That's first most important thing. There are parties who think we stop this. No, we should not. But what we should do is we should remove suffocating regulations. There's lots of things that we can get rid of very easily and that will enormously speed up the whole thing. You discussed this just about the Finanzamt. Yeah, that's one part of it. Stop state funding of implementation. We don't have the money for it because we need all the money in order to rescue us from the consequences of climate change. Mitigation, that is a way more important thing, not supporting green energy. Oh, thought I was too fast. Replace unrealistic targeting by explaining to the people the true urgency of action where it's working. We do not have to start with building hydrogen airplanes, so even Airbus has understood that. That is waste of money. We have other things to do that are more important. For example, build nuclear fusion stations. That is way more useful. And what we should do last but not least, we should, in the international regime, stop explaining other countries how it works. That is the worst thing that is Germany doing every day in the EU and also in other parts of the world. My boss said everything is interconnected to anything. Good point. It's not only technologically, it's also between society and politics and technologies. It's all interconnected. And Frédérick started with Goethe, so I end with Goethe. That's also a nice quotation. Better decide with uncertainty in the right direction than with certainty in the wrong direction. Thanks so much.
Yeah, we thank you for this contribution, and the floor is open for discussions.
Thank you for the very inspiring overview. My impression is that in the public debate on carbon footprint, a lot of attention is paid to cars. But when you integrate over all of the cars in the world, the CO2 output is less than 10% of the problem. Whereas cement production and long-term shipping, long-distance shipping are at least a factor of 3 higher. So two questions. What are the innovations we can make to improve cement and long-distance shipping? And second, why are we not talking about it? Why do we keep talking about cars?
So the second question is easier to answer. It's simply because not everyone sees cement production and large-scale shipping. So it is simply not present. We assume also fossil energy. No one thinks about how much infrastructure is in fossil energy. This happens in places where no one is living. And this is the same here. In cement production, this will be an eternal problem, and that is the reason why, and what I skipped is, of course, we need to circular economy in order to do something about this. But there will be a time in life where we'll be happy that we have cement because we need carbon. We are made out of carbon, and everything that is around us is made of carbon that will stay like this. So if there's no fossil energy left, we need a significant amount of carbon. Quite a few megatons, and they come, for example, from cement. I do not think that we can do much about the CCS. Yeah, I don't know whether this is a good idea. I do not think that there's enough CCS capacity only for the global cement production. And shipping, yeah, that's one of the applications. Methanol ships, you have heard this already. They exist already, and they will be the future. So the marketing, the big marketings of the producers of container ships, they all have decided it's methanol. So the debate whether this ammonia hydrogen is over, it's methanol is decided. So that's the solution.
Gauss?
Yeah, thanks a lot for this fabulous story. I have a lot of sympathy for that. What I always miss in these stories is actually one of the major components which is never really talked about. And that is, the challenge we are facing, that is 50% of our energy is actually used for heat. And heat, of course, is an ideal energy which you can produce via geothermal production, and we have plenty of different means of doing geothermal project developments anywhere in Germany, Europe, and the rest of the world nowadays. So technology-wise, it's absolutely no problem anymore to do that. And cities like Munich have already an energy production or a heat production which is above 50%, and they will be the first city in the world, mega city in the world, which actually will be neutral with respect to heat generation via geothermal energy. So in none of these slides was actually the mention of geothermal heat and geothermal energy production in there, and how to actually stimulate that and develop that on a large scale around the world, not just in Germany.
Germany is anyway not a good place to do that. Now, there is, I mentioned already this little box, thermal storage. Yeah? There is an enormous amount of activity there. You're perfectly right. I skipped this simply because this is a huge area in its own right. And it is clear for house heating and so for low temperature heat, so heat pumps and geothermal heat, any connection between air and underground will definitely be the future. There is no doubt about this. But that's happening already. So this is done. That looks very much different when you need large quantities. So again, in Germany, where I have high technology, I can afford big heat pumps that take this out, that's okay. But in the world, that's not a solution. So we need additional things. We have in southern parts, we have solar energy, and of course we can also store solar energy in thermal storage. So thermal storage is a huge thing by its own right, but it is flourishing, it's coming along. And I think I did not pay any attention because for time reasons, not because it's not important. What I want to say is that there is also risk associated with this. This is in particular deep geothermal generation. In southern Bavaria, there is a good example of that. So they drilled a big hole and they took out high temperature water there, about 180 degrees hot or so. But they had a problem with the piping, and then the hot water went into in an underground layer that is gypsum. And this gypsum started to grow because, of course, it was fixed. The consequence of this is that this village where they did this is now 4 meters higher than it was before, and half of the houses fell apart from it. So yeah, but also this super safe technology also has its risks. That does not mean we shouldn't do it. We can also get lithium out of this. We can do 1,000 different things with geothermal. But this is a whole thing in its own right. This is not done in 2 minutes.
Two short questions.
Thank you. We heard about cement production. The same global emission that cement production is producing is actually produced also by deforestation and land use change.
Correct.
We shouldn't forget about that. Stopping deforestation means immediately 10% reduction of global emissions. Point number one. Point number two, I'm very thankful that you mentioned the heat pumps, because we have heard a lot of numbers. 1 kilowatt hour into electricity into a heat pump gives me 5 kilowatt hours of heat. We shouldn't forget that.
No answer necessary. Tick mark.
Frédérick?
Thank you. I basically agree with everything you said, Robert. I just want to highlight one point you have on your last slide. Alles hängt mit allem zusammen. You said we would need to convert the chemical industry. We would need about the electricity production of Germany, which is a figure for comparison. But currently, our chemical industry gets their input from all over the world. And I think in a new system, we would do the same. We would produce methanol where it's cheap to produce, ship it like we do it nowadays with the oil, and use that as the input instead of the naphtha. So we wouldn't need to increase here in Germany. We would have a global market like we have with all the things, I think.
Agreed upon. A significant fraction, however, of this energy is still local, because it's considered e-steam and all these things, so process energy. It's about half of this 500 terawatt hours. That is local. But raw material, agreed, there is not, probably none of these raw materials will be produced ever in Germany, probably not even in Europe.
So
good point, thank you.
Question by Martin Quack, please.
One thing you didn't talk about in your great global picture is what I would call reverse fossilization.
using biomass in order to collect CO2 and then trying to remove it is principally a good idea. To do this in global dimensions, we have this problem of emerging climate change. It's not so easy. We will expect an enormous deforestation from climate change anyway, because we know that the rainfall pattern will change, and a very large amount of rainfall that is now on our continents will fall in the Pacific Ocean in the future. That we know already. So be careful. If you need water to irrigate forests in order to collect CO2, I think that is not a good idea. So we should be careful with this biomass story, because we always think the biomass distribution on our planet will be as it is today. And this is absolutely sure that this will not be as it is today. We would use then artificial biological systems. Yeah, that can be done. But until you need gigatons of CO2 collection, it's still quite a job to do. Yeah, but the amount of carbon in all marine systems is so pretty low. It's 5 gigatons. That's nothing. So we always think there's all this algae and all these things, but it's very little carbon that is in there. We can also think why, because there's not enough oxygen and no light in the deep ocean, so that is why it's so little. Is this all working? And these are contributions, and who am I to say this is not useful? But we have to think about the big picture. And the big picture really means we have to stop using fossil energy as quickly as we can in the large applications. And the largest application is first power. So coal to power is just a no-go. And the second thing is heating. These are the two big things. And then we have already done half of it. Okay, or more than half of it. That's probably enough in order to stabilize our climate. We should not start with the most complicated things in the beginning. That is also, this is typical Germanic idea. We start with the 100.5% solution at the first day. Yeah, it's exactly that. That takes longest and costs most. That's not what we should do.
Well, I think these are good final words from you, Robert. So please join me in thanking Robert and all the speakers.
Just a few final words. When a year ago we thought about this event, planning a meeting on hydrogen, it was something very different. And I have to say, this was a fantastic event that, by chance, without foreseeing it, has happened by uniting the diverse sections of our class, collaborating with the class on biosystems, and having this fantastic, multifaceted, as well as fascinating range of topics that we were discussing, all basically triggered by the topic of hydrogen. Who would have thought that a single topic has so many fantastic, spectacular facets? This is something that's going to keep me awake a long time tonight, I'm sure about that, but that hopefully also will trigger a lot of discussion in the ongoing evening and maybe in the future. I see that there is many large open questions in virtually all the topics that we have been talking about. Most of these topics I'm fascinated also to see are they're multidisciplinary, really. They go beyond our traditional disciplines and require us to develop cross-disciplinary initiatives to really address them. That's a challenge. We know all of this, and it might be a thought, even use part of the evening dinner to think about such potential options for such collaborative initiatives, moving beyond disciplines to get at the solutions that we desperately need. From Big Bang all the way to addressing the energy transition that we're dealing with. I can only end by saying, in the name of the organizing committee, a big thank you to all the speakers for these great talks that we've had the pleasure to listen to. So thanks again to all the speakers for this fantastic day.